So a good day to Dr. BC, and I'm going to present on assignment 2. So start with the introduction of my project. My project is actually a Cantonese opera hub located in Planning Street. So basically it talks about um, this Cantonese opera as a social connector of the area, and it is deeply rooted within the lives of the local Cantonese community. So it shows the importance of this Cantonese opera at Planning Street at that time. So the inspiration of the form is from this traditional bamboo theatre, and its construction logic is some sort of like a grid-like structure, and they also focus on some of the passive ventilation. So as you can see, this is the form of the traditional bamboo theatre. There's two types. This one is the big golden bell, and then the second one is the dragon boat shed. So looking into replicating the form of the bamboo theatre, I also look into the construction logic of the bamboo theatre. So for example, I study on the tying methods of bamboo. So you can see from this tying method is called bamboo scaffolding. So it is, you can see it's tying, it's like wrapping two horizontal, one horizontal and one vertical bamboo pole together. And then this second tying method is called the tightened bamboo scaffolding, and it is also involving like twisting and wrapping the straps over uh the two bamboo poles. So this construction logic in the whole is more towards like nailless and also twisting method. That's what I'm looking for in my case study. So my case study direction was starting with the inspiration from bamboo theatre. Then I studied on the construction logic of nailless and twisting construction method, and also its grid-like structure. I also look into replicating the passive ventilation via stack roof. So for the nailless and twisting construction method and grid-like structure, I'll focus on a case study of GC Prostal Museum Research Center by Kengo Kuma, and then this passive ventilation will be focused on RE residents. And then from these case studies, I'll then implement their building technologies to this real life case study in KL, which is this Yankang Dramatic Association building. So for my case study one will be on nailless and grid-like structure. So this case study is by Kengo Kuma from the GC Prostal Museum Research Center. So its concept is a fusion of traditional craftsmanship with contemporary design, and it is a combination of public and private spaces. So these are the exterior facade and structure, and you can see it also continues to the interior space and accesses storage. So how they construct it is through this Sidori system. Is basically actually a small scale toy inspired by a Japanese toy, and it's a 3D puzzle that joins the wooden sticks together by twisting. So it doesn't require any adhesive or mechanical fastener to join. So the original Sidori size, cross-sectional size is actually 12 by 12 mm, but then in this case study, they actually enlarging it to 60 by 60 mm. So you can see how they fit this wooden pole into one kind of like matrix. So they actually twist the wood into like some kind of like this structure you can see here. So the construction method of a larger scale Sidori system. So this part is prefab offsite. So first they join like two structural members together with a 10 mm thick timber connector by Zakova, which is a type of tree. And then they use like this connector to like kind of like join these two structures together. And after joining these two structures, they actually join another two on top. So a grid member is formed when four timber members are joined together. So this is prefab offsite. And then after that, they assemble each of these grid member on site. So you can see in the end it becomes like a whole structure itself here on site. So construction details of Sidori system to walls and floors. So it's actually for this case study, it's actually a mixture of timber and concrete. You can see timber is around here and then concrete is right here. So mostly the timber structures is housing those more of public activities such as like exhibitions. And then the concrete structure is mostly on private research spaces. So you can see this is the connection of how they connect the wood structure with the concrete on slab and then on the concrete wall. So there's actually a little gap between the wood and concrete to prevent past invasion and water seepage, and also gives the wooden framework a feeling of floating in the air. Then this is the construction steps of building. So you can see it starts with a platform as a foundation, and then secondly, they actually carve out this shape um, as the main gallery space, and then thirdly, they actually built the private concrete spaces first as a framework, and then they added the cladding glass, and then in the fifth step they added the wooden Sidori structures around wrapping around the concrete, so making it more like warm instead of like using a concrete building over there. And then lastly they added roof caps to complete. So what are the feelings being inside this Sidori structure? So this space is actually an exhibition gallery design. It is defined by a carved hollow core within an even wooden grid. So this hollow structure actually gives a cave-like feeling, so you feel very quiet and calm inside. And this story structure actually extends up to the basement, so it penetrates downwards into the concrete areas. And then this part also becomes a part of the light well system. So I actually looked into how this storage system helps to improve the um, climatic response of the site. So you can see from this plan, this structure is actually placed facing the sunward, the sunlight direction. So it is, I assume it's used as a shading device that is similar to the egg crate shading device. So I looked at the shading effects of an egg crate shading device. So from this study, it shows that the egg crate room actually shows a 58% lower radiation penetration compared to the normal one without the egg crate. And then this egg crate room also shows a 1.7 degree lower temperature. So in conclusion, this egg crate shading device is effective in provide sun shading and lowering the temperature of the indoor spaces. So you can see this is a crate shading device and also see the resistor, which gives a similar effect for the case study. So in back computing performance, we look at the visual response first. So psychologically, it this door system actually reduces glare and softens the natural lighting into interior spaces. So you can see it gives a similar effect like you're in a forest because it filters strong light penetrating to the building. Psychologically, it gives a calming effect because it reduces the eye strain and fatigue, and which it is also very crucial for having this kind of effect in a viewing exhibition. And then sociologically, it actually enhances the wayfinding, creates a feeling of being safe to navigate their way in and out because this security system actually is semi-transparent, so you can see the inside from the outside. Then thermal response wise, physiologically, it helps to maintain the thermal equilibrium of the body, which prevents heat exhaustion. So this wooden lattice structure, it actually functions as a crate system that reduces indoor air temperature. Psychologically, it reduces irritation, stress, and distraction, which is crucial for the museum spaces in this building because of it being thermally comfort, it helps to maintain the well-being and also stabilizes the mood of the user. Sociologically wise, it helps to cool indoors, which allows longer public engagement and social interaction. So for the next case study, I'll focus more on the passive ventilation system. So this case study is RE Residence by Michelle. And then the design goal is actually wanted to create a customizable evolving home, matching a dynamic lifestyle. So they wanted something that is simple and low tech and that can adapt to any climate and any user and any activities they want. So this is the openable wall panels. These are the features that they have to achieve the passive design. So first is the openable wall panels you can see here. And then secondly is the openable ceiling system. So you can see during some days, this wall panel are closed. And then this is when the wall panel is open. So you can see the different effects that to the building exterior. And then this is when the ceiling panel is closed and when the ceiling panel is open. So looking at the openable, these two operable systems, how the mechanism works. So for the ceiling, it is using the manual linear actuator. So it actually, the user have to pull the chain and then the wheels will turn and then the ceiling blank will open. Then for the lift door system is much more easy and simple, which uses the gas hydraulic strut with lift hitch piston arm, which is commonly used in cabinet doors. So when you open, it actually lifts like slowly and softly. So next is the construction method of the building. So you can see it's using this wagayo framing system, which is a traditional Japanese roof framework. And this is the diagram showing how load is transferred from this structure towards the posts. And then this is the sectional view of the wagayo framing system. So these are the elements of the wagayo framing system. And then material wise, for this building, it's the upper part, which is the roof, is using the FRP because it's lightweight, can span longer distance, and also it's weather resistant and non-corrosive. For the wall material, it's using metal because it's visual and tactile contrast comparing to the upper part of the roof, which is semi-transparent. So this combination from exterior, it looks very traditional, but the material choice is more give it more like a modern feeling. So it gives like a visual contrast. So for the interior space, they are using the concept of flexible interior layout. So you can see the one labeled in yellow is actually fixed, like for example, toilet and kitchen, which use concrete. And other spaces are open and flexible, so they can easily like reconstruct their own activity spaces based on their liking. So these are the flexible spaces you can see here, and then the fixed one, which is made out of concrete. And then the surfaces wise, for this building, you can see it's aligned along the glass ceiling at the center. And then some of the negative, not so good example ones are, you can see the wirings are hanging at openable ceiling, hanging in the air. So one of the design considerations that we can have before constructing this building is pre-planning of this wiring, so to like prevent this kind of mid-air hanging wiring around the building. And then we have to coordinate before construction to avoid any disruption in spatial clarity. So looking at the passive ventilation system. So it's more unnatural ventilation. So the side context is they have a contrasting summer and winter climate. So they combine lead doors, operable ceiling, and also attic ventilation fan. So in summertime, the ceiling is closed, and then the sunlight actually transfers heat from the roof to the internal spaces. So this space will be very hot. So they close the ceiling part, and then heat is trapped here. So they use the exhaust fan to suck out the heat out of this place, and then and then they open the lid doors to allow wind to enter from body level. And then at night time, they open up the ceiling, and they allow this wind at body level to enter towards the ceiling level, and then exit towards the exhaust fan. So it gives a more exchange of fresh air towards inside all the interior spaces of this building. So during the winter time, they close the lid door and they open the ceiling. So when the light transfer heat from the roof towards the interior, the lid doors will actually trap the heat to maintain warm during winter at daytime. And during the nighttime, because there's no sunlight to penetrate towards the roof area, and then they want to confine heat at a certain space, so they close off the ceiling and the lid door to trap the heat only at usable spaces, which is the ground floor. And then we look at building performance visually. So in psychological aspect, it actually helps to reduce glare, and it provides adequate illumination to boost productivity because of this semi-transparent FRP roof that allows daylight penetration. Psychologically, it helps the user to feel more secure inside the building because of the transparent FRP. They actually can tell the time based on lighting conditions. And sociologically, it gives a sense of place and security because occupants can actually see the rhythm of light and shadow. Thermal response wise, we look at the physiological aspects. So it helps to reduce the risk of sick building syndrome due to the hot weather that builds up heat because of the operable lid doors and also operable ceiling. Psychologically, it gives a feel of sense of individual control because the users are able to shift their feeling of spaces and control the thermal conditions of the building with the use of lid door and also operable ceiling. Sociologically wise, it gives the effect of boosting positive experience because of being inside a thermally comfortable space. Looking at building integrity, physiologically, the Wagoyo framing system is actually a system that's widely used in Japan. So occupants will actually feel safe staying inside the house. Psychologically wise, it is also similar to what I've mentioned. So because it is known, Wagoyo framing system is known for its resistance to structure failing. So occupants will actually feel safe because of the reliance and of the Wagoyo framing system. And then economically wise, because they use the FRP roof and timber, it actually minimizes material costs and the passive design strategies are low tech. So for the case study, we more focus on implementation. So the implementation is on this Sankan Dramatic Association building in KL. It is actually constructed in 1920 and used as a performance hall for Cantonese opera. It is located near to Petaling Street. So this is the history and background of the building. So at its peak, it actually reaches up to 13,000 members. And then after the golden era, the current status now is the association is inactive and only around like 100 elderly members remain. So the location of this building it's located here, and this is the Jalan Petaling. So it is actually only a 2 minutes walk from Petaling Street, and then from Guan Hong is only a 4 minute walk. It is actually positioned at the edge of historical building zone, so you can see a Merdeka 118 tower behind this building. So the issues of this building is visually, it has a low natural lighting, so it makes the space feel small and enclosed because there's no skylight or opening, and that you can see a very dim interior that relies on artificial lighting. So all of these issues actually causes fatigue for both performers and audience, and the space feels disconnected from the outside world. It also weakens the visual emotional impact of the opera performance. So one of the solution, so this is a existing condition. You can see the one labeled red is enclosed walls, and you can see light is not able to penetrate towards these enclosed wall. So one of the solution is by incorporating Sidori walls to transfer this enclosed wall to more of a semi-enclosed space. So it allows the sunlight to penetrate towards the interior spaces. It also helps to filter the strong light into more of like a soft lighting for the opera performance. So you can place the stage around this area, and then the audience will sit around this area. Next is the thermal performance. You can see the issue is lack of natural ventilation. So because it's like a traditional shophouse design, so hot air is actually trapped here and also here because there's no cross ventilation, and the windows are only facing one side. So there's minimal fresh air supply for this large audience. So heat will actually build up in this area, making the space uncomfortable and also reduces the audience concentration. So the overall thermal discomfort actually will weaken the performance experience. So this is the proposal of incorporating the theory structure along with operable ceiling, openable wall panels, and also a mechanical vent. So you can see it allows the cross ventilation and enable fresh air to enter from either of the direction. So in conclusion, some of the recommendations is some of the lessons learned is that the modular and lightweight system enhance visual performance. By using the Sidori system, it helps to reduce glare and heat, improving spatial quality. Next is the operable elements that improve thermal comfort without using high-tech system. So as shown in every residence, they only use like operable ceilings and wall that can enhance natural ventilation. So they won't need to rely on mechanical systems. And also these systems are low-tech and easily operable by anyone. Next is the material selection that affects the structural performance and perception. So by using FRP roofing and cypress timber, they, they enable longer span, soften the daylight, and weather resistant. So it helps to balance the tradition with the modern structural needs. Lastly, is on recommendation. So it is recommended to integrate grid-based timber system to improve visual depth and lighting. So these theory systems are actually prefab and reversible, so they do not alter original walls. Next recommendation is using hybrid material for structural and environmental optimization. So with combining steel with timber or FRP, it creates a strong light and thermal comfortable spaces, which is very ideal for Malaysia's climate. The third recommendation is to adopt operable wall and ceiling system for passive ventilation because these systems are simple and they help to cut up heat build while using a low-tech and user-friendly system. Lastly is a reversible and modular design for heritage. So using a non-invasive and prefab component such as the Sidori system, it respects the heritage while supporting adaptable cultural use. And that's all for my presentation.